We begin this week by going over an application of the Cauchy criterion for sequences, but applied to series. This is theorem 2.7.2 in the book on Cauchy criterion for series. And what does it say? It says that the series sum from k equals 1 to infinity of the a sub k, some series converges if and only if for all epsilon greater than 0, there exists an n in n such that for all n comma m greater than or equal to n, a sub m plus 1 plus a sub m plus 2 up to a sub n in absolute value is less than epsilon. Here, well, probably we need to assume that n is greater than m. Yeah, for this expression here to be to make sense. If not, well, then we need to start with a n plus 1 up to a sub m. To have at least one term. So what is it called, the Cauchy criterion for series? The reason for that is because it's just the Cauchy criterion for sequences. It's just that we're looking at particular kinds of sequences. Those that arise from adding numbers up to a certain point. So we recall that Sn is the sum from k equals 1 up to n of a sub k. And everything that, all the statements that we made about the convergence of series have to do with the convergence of the associated partial sums. So the partial sums are sequences of real numbers, and if they converge, then we'll say that the series will converge, and if the sequence does not converge or diverges, to use the terminology that we introduced a while back, then the same will hold for the series. So understanding this, we know that for any sequence, so sequence in R, for any sequence in R, so a sub n, remember that if we know that this goes to 0 as n comma m go to infinity, this is another way of saying the same thing. The sequence is Cauchy. This implies that an is convergent And this is the statement for an arbitrary sequence an. Probably should have used a different kind, a different thing, so not to confuse with the a case. So the bn's, the sequence of bn's is convergent, and that's all actually is all we need. The sequence of partial sums here is going to be Cauchy, sum from k equals 1 again up to n of the a case, minus the sum from k equals 1 up to m of the a case, it's less than epsilon. But this inside is exactly the same as the sum from k equals m plus 1 up to n of the a case. So if you notice that here we're adding all the numbers of the a's of k's from k equals 1 to n, in the other term here, this other term is adding everything from k equals 1 up to m. So the first m terms will cancel out, and what you'll be left with will be the sum of the a k's from k equals 1, m plus 1, I'm sorry, from k equals m plus 1 up to n. And this is exactly what we have here. We're adding all the terms from m plus 1 up to n, so the a sub m plus 1 plus a sub m plus 2 up to a sub n, and that's less than epsilon in the end. And so that's why I said, this is just an application, a straightforward application of the Cauchy criterion for sequences. It's nothing more than that. So if you write everything down and you take the time to see what everything means, this is just an application of that. So one important consequence, they give it as a theorem here, but I don't think it deserves the name of a theorem, title of theorem. It's just a simple corollary. And it's the observation that if you have if your series is convergent, then the nth term must be going to 0. So that you must be adding numbers which are going to 0. And for the proof, we just need to appeal to theorem 2.7.2. Here, remember that we know that there is an n such that if n is greater than m and both numbers are greater than or equal to n, to this capital N, then the tail here, not the tail, no, so the sum of the terms from going from the m plus 1 term to the a sub n is going to be less than epsilon for it. But the crucial thing here is that this is true for any n greater than m greater than or equal to n. So this holds in particular when n is equal to m plus 1. So we give ourselves epsilon greater than 0, and so given we know there exists an n in n such that for all n greater than m greater than or equal to n, the sum from k equals m plus 1 up to n of the AKs is less than epsilon. So this is true for any choice of n and m, provided they're both greater than or equal to capital N. And of course n greater than m is just a restriction, so that allows us to write this thing in a simple way. Otherwise we would have to separate things into cases. So this is not really a restriction. The restriction is that both numbers have to be greater than or equal to n. And then we're able to conclude then that this sum is less than epsilon in absolute value. But in particular, we have if m is greater than or equal to n, a sub m plus 1 is going to be less than epsilon. Right, because m plus 1 satisfies the hypothesis, so m plus 1 is greater than m, and m is, by assumption, greater than or equal to n. So you can apply the previous theorem and conclude then that this the sum of the terms between m and n, and since n is just m plus 1, there's only one term. So I mean, you only have a sub m plus 1. This is the first number greater than m, and it's less than or equal to n in this case. And so you can conclude that that is less than epsilon. So you have, so going back, remember to always check what you've shown and compare it to the definition of convergence. So given epsilon greater than 0, so you start with that. So to prove a statement about for all epsilon greater than 0 that something happens, you start giving yourself an epsilon greater than 0. And then you conclude that there's an n, or an n plus 1 if you will, because this is what we're going to use, such that for all m greater than or equal to n plus 1, because you can write this m plus 1 as just some m bar, the absolute value of a is a sub m plus 1 or a sub m bar, as I said, is going to be less than epsilon. And that's the definition of convergence, in this case to 0. So you're really showing this for all m greater than or equal to n. So which you can write as for all, say, n greater than or equal to n plus 1. This holds. And this means that n converges to 0. That's exactly the property. That we wanted to prove, so that the ANs actually converge to 0. Okay, so then be very careful when you apply theorems. You have to keep track of everything that you're doing, so you're able to compare that with the statement you want to show. Remember, you want to show that for all epsilon greater than 0, there exists some natural number n, such that for all natural numbers n greater than or equal to that capital N, the number a sub m a sub n, or a sub n plus 1 in this case, which is what we use as notation, is less than epsilon, that the number in absolute value is less than epsilon. Because that shows that the sequence converges to 0, which is the definition. So if you keep in mind the definition, then you'll see what you want to show, and you'll be able to use the hypothesis of the previous results to conclude. In this case, I mean, it's just a very simple application. Just choose n to be equal to n plus 1, and that's it. Okay, so then that's a proof of that statement. And one little remark. If this is what we've just shown. We've just shown that if this series converges, then a sub n goes to 0. N goes to infinity. This is the content of theorem 2.7.3. This is exactly what we just proved. However, so this is statement P, say, okay, I mean the series converges, then Q, an goes to 0 as n goes to infinity. But however, the converse is not true. So if an goes to 0, that doesn't mean necessarily that the sum converges. Okay, so it's and yeah, so this is one of the important things you need to remember. So you've just shown one implication to one side too. So so from P you can obtain Q, but not you cannot obtain P from Q. So the fact that sequence goes to 0 doesn't mean that you will be able to add the numbers and expect to converge to expect to have a convergent series from doing that. And just remember that, I mean, the trivial example, so let me just erase this. So think of an equals 1 over n, so the harmonic series. So we know that this series diverges already. I mean, this is what allowed us to construct rearrangement of the alternating series, so that the series where we don't consider instead of considering 1 over n, we consider 1 minus 1 to the n plus 1. And when we add these numbers, we can find rearrangements so that the sum converges to whatever value we want. And that relies on the fact, so rests upon the fact that this sum here diverges. So it is not true. So even though when a series converges at the nth term of the nth term you're adding is going to 0, must be going to 0. So the sequence of those numbers must be converting to 0. It's not true that if you have a sequence that is converting to 0, that has to give rise to a converting series. Okay, so that's one thing. Now, the next thing is theorem 2.7.4, which is the comparison test. So here we assume, so the idea is to obtain the convergence of one series from the convergence of another. So assume we have two sequences, AK and BK. Are sequences satisfying that, well, all the terms AK and BK are both non-negative, but the AKs are bounded from above by the BKs. Holds for all K's in N. Then we can say two things. I mean, the second one is actually equivalent to the first one. So if the sum of the BK converges, then so does the sum of the AKs. If instead the sum of the AKs diverges, then the sum, so the series of the BKs diverges. And yeah, so what I just said was that these two statements are actually equivalent. So you think of BK, I mean the sum of the BKs converging, so the series of the BKs converging being a statement P, then the statement that the series of the AKs converges is a statement Q. The first one is telling you P implies Q, and the second statement here, so the second conclusion of this theorem tells you that not Q implies not P. Not Q being that the series of the AKs diverges. Okay, so P and Q, P implies Q, and then Q implies not Q implies not P. So they're both equivalent. So there's nothing. There's nothing to be said here. The one thing, actually, well, the proof they give in the book is kind of strange. I mean, all these numbers are non-negative. So what you can say for sure is that since the sum of from k equals 1 to a certain number m of the AKs is less than or equal to some number, maybe some number n, is less than or equal to the sum from k equals 1 to n of the BKs, because remember, each bk is greater than or equal to ak. And you know this is bounded from above, right? So this is bounded from above by the whole sum, so the series. Because you know the series exists, so this thing here converges. And in fact, it's bounded from above by the limit of that sequence because you're only adding non-negative numbers. And also you know that this is bounded from below by 0 because you're only adding non-negative numbers. And so this sequence here, this Sn, is monotone. This sequence here is monotone, and it is also bounded from above by this number here. Remember, this is a number. This is the limit of this sequence here of partial sums for the BKs, because you're assuming that the BKs are summable, meaning that the series associated to the partial sums of the BKs converges. So we know that this Sn is monotone, is bounded from above, so that means that Sn converges. But this is the same thing as saying that the series is convergent. Because the series is if it exists, it's the limit of the partial sums. Okay, so the Sn converges then if the series of the BKs is convergent. As I said, the second statement follows from the first one. So the second statement follows from the first one because it's actually an equivalent statement. Okay, so this is the proof of this small, well, it's called a theorem, but it's just so small observation. So now, important series, something that we covered at the beginning of the course. This is example 2.7.5. It's the geometric series. And for that, we introduced what the notion of geometric series is, something we've already talked about, and you've seen it many times before. So if it is of the form a times r to the k, where k goes from 0 to infinity, so a plus a r, a times r squared, etc. Naturally, of course, you can see right away that if r is equal to 1 and a is not equal to 0, then just be adding infinitely many a's, and so the series diverges in this case. We had already seen that we can obtain an explicit expression for the partial sums here. If we remember, if Sm is the sum from k equals 0 to m of a r to the k, this is equal to a times 1 minus r to the m plus 1, all that divided by 1 minus r. This expression is valid whenever r is not equal to 1. It doesn't matter whether r is less than 1 in absolute value or not. The only requirement for this expression here to make sense is that the r is not equal to 1. Because you see, you will get an indeterminate form. The top and the bottom would become 0 if you try to plug in r. For all the other values of r, this expression here on the right makes sense, and in fact the derivation, you can see that you can the derivation of this formula is actually valid, because the only thing you need to do is to be able to divide by 1 minus r, which is allowed as long as r is not exactly equal to 1. Now what you can see then is, okay, you have two situations. Either r is, three situations. Either r is 1, in which case the series clearly diverges, or you can split into two further cases. One where the absolute value of r is less than 1, in which case if the absolute value of r is less than 1, then you can see that the Sm converge. The Sm converges to the sequence of the Sm converges to a over 1 minus r. Why? Because this term here is becoming really small. Remember, the r is smaller than 1 in absolute value. Then this is going to 0 if r is less than, the absolute value of r is less than 1. You're raising something that's smaller than 1 to an arbitrarily large power that's approaching 0. Okay, so this holds if the absolute value of r is less than 1. What happened to my minus here? If not, so if the absolute value of r is greater than 1, then the same term here, the r to the m plus 1, is going to infinity, so the whole series is divergent. Okay, so either R is equal to 1, in which case the series diverges. If not, if the absolute value of R is less than 1, then the SM converges to A over 1 minus R. And if not, then if R is greater than 1, then the sequence is divergent. Well, let me just say that the series is divergent then. Here, though, we are in the case when A is not equal to 0. When A is equal to 0, then the series is just 0. So it's converging everywhere. So if A is equal to 0, then it's identically equal to 0, therefore convergence. Regardless of the value of R. Okay, so as we've seen, then we can study geometric series completely. We understand them completely, and because we do, we're gonna use it to derive statements for other series, because we know what happens to the to the geometric series in all cases for all values of A and R. This is what we're going to be doing next. We derive a criterion for comparing two series. So if we knew that one was convergent and the one was bigger than another one, term by term, then we can conclude that both things converge then at the same time. Then this is what we're going to use for comparison. So this is one series that we understand in all cases, and we're going to be using that in order to prove that some things are convergent as well. Okay, so that's going to come next.